Okay, in this video, we're going to completely break down the transformer block. So we're going to explain how every single one of these components works. We'll touch a little bit on the embeddings and the final two layers, linear and softmax, but we're primarily going to focus on explaining the transformer block. So that's the attention, the add and norm, as well as the feed forward. We're going to break these down one by one, starting with the add. Okay, so the add actually refers to a concept called skip connections or residual connections, and here's how it looks visually. We have some arbitrary layer in a neural network. This might be a linear layer, this might be an attention layer, and it takes in some input x, which we can see over here. But instead of just taking the output of the layer as the output, we'll also let some portion of x actually completely bypass the layer, and it will get added to the output of the layer over here. So in code, if we were writing the forward method for some kind of layer and we wanted to incorporate skip connections or residual connections, we would actually return layer of x, so call the forward method for the layer, passing in x, but also add x. And just to get some intuition as to what this kind of means, is the model will actually learn the right weights and biases for this layer so that the right proportion of x is either sent through the layer or the right proportion of x is allowed to actually bypass the layer, right? Maybe we don't actually want to transform x based on this layer. Maybe we want to retain x's original identity and pass most of it, or at least incorporate it into our output for this layer. So the model can kind of essentially through training, through the minimizing of the loss, through the training data, figure out how much of x should be passed through and how much of x should be sent through this layer. That is some of the intuition for what a skip connection is doing. However, why do we actually need to do this addition? Because technically, shouldn't the model just be able to learn the right weights and biases in this layer to not change x at all? Something like this. Why do we actually have to add x to actually get this to achieve our desired results? Well, there's actually another big benefit of skip connections, and it's actually the main reason that they were originally added into these deep neural networks, and that has to do with solving the exploding or vanishing gradient problem. Exploding or vanishing gradient problem, or exploding or vanishing derivative problem. We know that calculating derivatives and gradients during the process of training is very important for gradient descent and minimizing our loss by updating our parameters. However, something that can occur with these super deep neural networks that have tons of layers, left to right, these neural networks have tons of layers, is that gradients can either become super big or super small. And if we recall our update rule for gradient descent, we know that for any weight or parameter in a neural network, the new weight is actually just equal to the old weight minus alpha, the learning rate, times the value of the derivative or gradient. And if this derivative value, if it's too small, if it's vanishing and going basically to zero, then this term is basically going to zero, and the new weight is almost the same as the old weight. So we're not able to update the parameter at all. Similarly, if this value of the derivative is way too large, then the new weight is going to be drastically different than the old weight, and that won't be great for the neural network's performance. So we would like to mitigate this problem in some way or another. And it turns out that this simple addition does end up reducing that problem. Because if we recall from calculus, if you have some function f of x, and it's just the sum of two other functions, g of x plus h of x, when you're actually taking the derivative, you can actually just say that f prime of x is g prime of x plus h of x. So when the model is actually calculating all the derivatives, when we call loss.backward in PyTorch, the model will actually have an additive term when calculating the necessary gradients for this layer. And that actually will significantly help with reducing the problem of the exploding and vanishing gradient. The fact that we're doing an addition instead of a multiplication, as that doesn't drastically compound and, either drastically increase or drastically decrease the value of the gradients as the network gets deeper and deeper. So the short answer is that incorporating some kind of addition seems to actually keep the gradient values from either getting too big or too small. And researchers have found this time and time again with neural networks, and that is why skip and residual connections are included in the transformer. So the norm in the transformer block actually refers to something called layer normalization. And this is kind of a module of its own in PyTorch that you can instantiate by saying nn.layernorm and passing in in our case, the embedding dimension. And when you tell a layer norm that you're passing in the embedding dimension, that is the dimension along which we will normalize. So what does it actually mean to normalize in statistics? It essentially means to recenter our data so that it all revolves around the mean. So it will kind of look like a bell curve. And the way that we can take a set of data points and make it have this kind of shape where the mean is the most probable data point, the way we normalize data is for every single data point X, you actually just subtract out whatever the mean is, and you divide by the standard deviation. And that kind of recenters your data around the mean and makes it look like that. However, this would kind of destroy the whole point of a neural network if there was nothing learnable or trainable about this. It's just a direct formula for this layer that restricts the output to be having this shape. So to still have the neural network have some sort of learning capacity, we go ahead and multiply for every data point this minus mean divided by standard deviation. We multiply by some other number, gamma, the symbol is not super important there, and add some other number, beta. And these two will actually be adjustable and learnable across the iterations of gradient descent that we perform. But the question should be, why does this actually improve the performance of neural networks? It has been found to actually increase the training speed of neural networks and make deep learning far more effective. And researchers are actually still not entirely sure why normalization tends to improve the training of neural networks. But their current hypothesis is that we know that the neural network starts off with totally random parameters, right? Totally random weights, and to some extent, our data could be random as well. But if during training there's drastic shift in the nature of the data, meaning it's the two main attributes that characterize data, right? The mean and the standard deviation. If this kind of changes drastically in random ways, then the neural network training tends to be really slow and just not as effective in terms of convergence. So by kind of centering it around the mean, around the standard deviation, this is the standard deviation, and still by adding in some learnable parameters, so this isn't too restrictive, researchers have found that the performance of the neural network does increase, and that's why layer normalization is used in a transformer. One additional thing that I just want to clarify is what data we're actually normalizing. So to feed into this layer, we would have something that's T by E, right? T by E, where T is our time step or length of some kind of sequence, like our sentence, say the number of words in a sentence, and E is something called the embedding dimension. So you can think of that as the size of the feature vector for every token. So let's say for every word, we had a vector that encapsulates the meaning of that word, and that was our embedding vector of size E or of size embedding dim. When we say we are going to do layer normalization, it means we are going to normalize the actual feature, not necessarily the time steps or the batch dimension. If we had, say, multiple examples being fed in and we had batch by T by E, but we're actually going to normalize along the embedding dimension. So for every single time step, we have a vector, and we're going to go ahead and normalize along that dimension. Okay, masked multi-headed attention. Let's explain how this works. So during the process of training, let's say we have an example that the model is being fed in. So we have this sentence, write me a poem. So we'll quickly explain what the masked part means. Because this model is always predicting the next token in the sequence, the model actually does not get to look at future tokens. So when the model is fed in a sentence like this, there's actually a few training examples within here that the model can see. The first one is that given write, me comes next. The next one is that given write me, A should come next. And finally, the model sees that given write me A, poem should come next. But the masked part actually means that when the model is making its next token prediction, given all the tokens before it, the model doesn't actually get to see what comes next. So if the model was tasked with predicting poem and the model had the context of write me A, in our code, in our tensors or our matrices, we would actually mask out the word poem so that the model cannot see the answer before it's actually made its prediction. So that's what the masked part means. Now let's explain the multi-headed attention part, which is definitely far more significant. So when the model receives a complicated instruction like this, the model needs to know what part of the input to pay most attention to, because not all words in this input are equally as important. And moreover, there are actually relationships between every pair of tokens. So we know that this pair of tokens, write and poem, there's a strong relationship between them. Because what are we writing? We're writing a poem. The model needs to pay attention to that. We're not writing a book. We're not writing a script. We're not writing a movie. The model needs to know what to write. So this is clearly an important pair of tokens. So what attention does, attention is the model actually letting these tokens talk to each other. And every single pair of tokens will be considered until the model has actually figured out which pair of tokens are important and which ones aren't important. And then the model is actually able to generate some sort of new feature vector instead of the embeddings that were initially passed in. The model is now able to know the important parts of the input to focus on. So attention, if we had to summarize it, attention is a communication mechanism. Attention at a high level is the model letting the tokens talk to each other until the right relationships between them are learned. And the multi-headed component actually refers to the fact that this attention process I just described will actually have the model perform the attention layer on the same input. So we have the same input going into this attention, the same input going into this attention head, as well as maybe further attention heads. We might have 3, 4, 5, or 6, and so on. And what the model will do is it will actually just go ahead and concatenate the output of all the attention heads and pass that in to the next layer of the neural network. So attention is a highly powerful mechanism for the model to gain a deeper understanding of language. And because it's so powerful, we actually want to have many different heads that each learn their own weights and each operate on the input. This head of attention operates on the entire input, and it actually gets to learn its own weights and biases. The entire input is also passed in to this head of attention, and this head of attention learns its own set of parameters. So by exploiting multi-headed attention, the model is actually able to learn and understand language at a far deeper level. Okay, feed forward. Feed forward might actually surprise you that it's extremely simple. Feed forward is just a traditional or vanilla neural network. It's a vanilla neural network. That means there won't be any attention in this neural network. There won't be anything complicated except linear layers. So linear layers with an arbitrary number of nodes or neurons, as well as we'll have some nonlinear activations like the ReLU activation, and we may have dropout as well. But it is still a traditional, fully connected neural network when we do toss in some nonlinearities and some dropout. And it turns out that first having the attention and then having this linear neural network that essentially just does a bunch of computation, a bunch of weights, biases, and a bunch of matrix multiplication that essentially is, remember, just doing linear regression. It turns out that first having having the communication in the attention layers, and then after these tokens have paired up and essentially the model has figured out which tokens are relevant to focus on, then doing a bunch of computation, essentially a very complex mathematical formula, figuring out those weights and biases after. This is actually highly effective for the model's performance and the model's ability to ultimately predict the next token. So the last part of the transformer architecture, and specifically the decoder, is actually the linear and softmax components. And if you're coding up the transformer block, you won't have to worry about this yet, but you absolutely will once you actually code the GPT class. So the whole point of that final linear layer in softmax is to actually get an interpretable prediction. So for that linear layer, it will actually look something like this. It would be nn.linear of the attention dim. So attention dim, as that's kind of the new dimension after we've done all of this attention after the embeddings. So it would be the attention dim, but that's actually not the most important thing. The output features, or the number of neurons in this layer, should actually be vocab size. And the reason for that is for every single time step that this model receives in, every single token in the input sequence, the model wants to predict what token comes next. And that's going to be a bunch of probabilities, right? So we want to get a vector of size, vocab size, where we can interpret each number in this vector, each entry in this vector, as the probability that the token or character or word corresponding to that index is going to come next in the sequence. And then to squash those numbers between 0 and 1 and actually make them all add up to 1 so we can interpret them as a series of probabilities, that's what the softmax function is for. And that will be the decoder transformer. So if you're following along with the code, you now have the information you need to code up the transformer block class, which will actually, you'll be given the multi-headed attention and feed forward classes. And then you can go ahead and code the GPT class, where you'll be given the block class, you train the model, and then we'll finally code up generate, where we will finally see our trained language model generate text that looks pretty good and pretty similar to English. So I'd recommend jumping into the code next.